Last time, we described the timing requirements of the flip-flop in the setup and hold time. In addition, we will put the static flip-flops as an example to describe why the setup and hold time requirement is a must. After that, we provided the dynamic timing analysis DTA for the static flip-flops, which might be sufficient or not. Therefore, perhaps we may need to explore other dynamic flip-flops. For example, choose single-phase clock TSPC flops. Before understanding the dynamic flops, let's review the static latch-based flip-flops, which are commonly used in a digital system for several reasons as follows. First, the transmission gate stack flop is simple and easy to use. Second, the static flops are reliable for storing and transferring data. Without input changes, the output may stay constant forever. Third, the static flop can operate in high-speed applications. But can we move the speed even higher? Or can we reduce the power at a higher speed? To be honest, to achieve a high speed and low power isn't easy because of its natural limitations. Think about the feedback images for 5 seconds. Right, we all agreed that the static flip-flops can hold their state robustly by using the feedback loops, which require more transistors. The more transistors will lead to more capacitive loading to slow down the switching speed and increase the CVF current or power at the same time. In addition, keeping the state stable causes continuous power consumption. In summary, even though static flops are more robust and less sensitive to noise and linkage, its high capacity leads to a higher power and low speed naturally. What can we do? Think about the dynamic flops for 5 seconds. Correct. If our goal is to speed up the flops and lower the power, we must do the opposite way of the static flops as follows. First, get rid of the feedback loop. Second, reduce the number of transistors. Third, the fewer transistors and simple structure makes the layout more compact owing to a smaller size or a high density in those flops. Therefore, the dynamic flip-flops can achieve a very high speed and low power at the same time, owing to a less capacitive loading and passive routing capacitance. To be clear, do you have any idea to come up with the requirements for dynamic flops? Think about the clock distribution image for 5 seconds. Bingo! To make the layout more compact, especially the clock distribution, we must apply a single-phase clock instead of the differential clocking or even multi-phase clocking structure. Also, to make fewer transistors, we could also use the stack device in an inverter with a clock switching to implement a simple dynamic stage with a single clock device. Think about your own single-phase clock latch for 5 seconds. Great. For a positive level latch, the CK must tie to an NMOS to be transparently high. As you can see, when the CK is high, the latches become 2 cascaded inverters, and the output equals the input in this transparent mode. When the CK is low, the latch disables 2 cascaded inverter and the output keeps the previous state in this hold mode. Obviously, if you swap the NMOS of the CK device to PMOS, then it became a negative level latch over transparently low. How about the single phase rising edge trigger D flip-flop? Right. Do you remember the operations of the rising edge trigger static flaps? For example, when the clock is low, CK to PMOS, the primary stage should be transparent to launch the data, and the last stage, CK to NMOS, should hold the previous state by ignoring the input data for sure. When the clock is high, all the operations are opposite. The main stage is holding the previous data, while the last stage is transparent with the previous launch data to the output Q bar directly. So the first stage is the sampling, and the last stage is the holding mode. But how do we make sure the output can hold the data not only when the CK is low? Think about the high Z of the PMOS at the last stage for 5 seconds. Good. We need to pre-charge the gate of the PMOS to be high, such that the last stage output will be high Z, PMOS off as well. So the CK tied to the PMOS gate at the second stage. To make sure the pre-charge activity don't mess up, the CK clocking should get off the NMOS as well. Then another NMOS is just pass the data from D to Q while the CK's rising edge occurs. Please be advised, there's so many TSPC rising edge trigger flip-flop, but the basic idea is similar. Hopefully, this case study shows you why we come up with this simple structure to meet the dynamic flop need. Let's review the TSPC rising edge trigger D flip-flop operations as follows, and see if that matches to our mental model in the design without running any simulation. First, when CK is low, the first inverter passes the D to be D bar at the output, and the second stage charges its output B to be VDD, which turns off the last stage VDD pad, while the CK turns off the ground pad. Therefore, the output QB is in high Z mode and holds the previous state. When the CK changes from low to high, which is rising edge, if D was low before, then the A will be high, such that the second stage pull down the output to be 0. Then the Q bar of the last stage will be charged to high, which is inversion of the D, so we call the output Q bar. On the other hand, when the CK changes from low to high, rising edge, if D was high before, then the A will be low, such that the second stage keeps its previous output high in the pre-charge phase. Then the Q bar of the last stage will be discharged to low, which is also the inversion of the D high. After understanding the TSPC flop operations, we should appreciate all the charge dynamic operation to speed up the data sampling and transfer. But there's a fundamental design pitfall. Think about the linkage image for 5 seconds. Bingo, the TSPC flops will fail at sufficient low clock frequency because of the comparable high linkage. For example, if the clock period is very long, the Hall charge would be lost through the transistor linkage path from its substantial conduction. Then, the source and drain junction crops the stored state. The linkage issue is serious in the fast corner, high temperature, and high supply voltages. For example, fast 125 degrees C, supply plus 10% or even 15%. Therefore, unlike the robust static flaps, the dynamic TSPC flaps has the low limit of operation frequency, and that's the reason the TSPC are only applied to a very high-speed block, not all the digital blocks. Here are the summarized images showing you why we may need the dynamic or TSPC flip-flops besides the static flip-flops. Even though the static flaps are very simple, robust, and easy of use in all digital systems, it may not achieve enough high speed and consume too much power overhead. The speed and power limitations come from the feedback and complexity in a big amount of transistors and two-phase clocking. To speed up the flaps and lower the power, we may remove the feedback retention, use fewer transistors, and apply single-phase clocking. Then, not only the dynamic flaps is simple, but also the layout is compact to reduce the overall capacitance and power. Then, the overall speed can be boosted easily. We show the TSPC latch and TSPC flaps from the design idea for its operations. According to those concepts, you should be able to come up with your own and other similar improved dynamic flaps. But you must watch out its limitations or pitfalls in design at very low clock frequencies because of the linkage from the transistors. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.